Howdy, welcome to Chapter 10, Controlling Microbial Growth in the Body using Antimicrobial Drugs. So, check out this cute little cartoon. So this guy in the middle is a virus, and then the other guys on the outside are different bacteria. I don't think there are bacteria with 3 eyes, at least not any bacteria that I know of. So antimicrobials is a general term. Antimicrobials are used for treatment of disease, and they include antibiotics, semi-synthetics, and synthetics. So those are all types of antimicrobial drugs, or commonly known as antimicrobials. So antibiotics, that's a type of antimicrobial. It's made by microbes naturally. So for example, Bacillus licheniformis secretes a compound that inhibits the growth of other gram-positive bacteria. So an antibiotic is against a bacteria, and bacteria are doing battle with each other, so they try to secrete things that will inhibit the growth of other bacteria that are competing for that same area. And you can get these antibiotics from the bacteria to treat bacteria that you don't want as a human. The next type of antimicrobial is called a semi-synthetic. So what the scientists do is they get an antibiotic, so that's a natural compound made by a microbe, a bacteria usually, and then they chemically alter it. So they grow the microbial culture, and then they get the compounds that the microbes are secreting, and then they modify them, and usually they use semi-synthetics as oral medications for humans. And then synthetics are a type of antimicrobial that are wholly human-made in the lab. Antimicrobials have this thing called a therapeutic range, and that's the range of concentrations at which the antimicrobial is both effective and non-toxic to the patient. So you could have an antimicrobial drug at a really high concentration, and it's going to be effective, it's going to kill the microbes, but it's also going to be toxic to you. So you want to find that therapeutic range of the drug where it doesn't hurt the patient, but it does kill the microbes. So history of antimicrobial agents. This guy, Paul Ehrlich, he thought early on that he could find a chemical that would selectively kill pathogens and wouldn't hurt the host. And he called that a magic bullet. And I don't know that they found really any magic bullets yet, but hopefully they will. So at the beginning of the 20th century, that's last century, physicians couldn't do much for their patient. They just could say, well, your daughter is going to die in 2 months or whatever. And this is a photograph of a gravestone of a child from the 20th century. Scientists knew about the germ theory of disease, but they couldn't really do anything about it. And at the beginning of the 20th century, about 1/3 of the children born at that time died from an infectious disease before the age of 5. So this is a table of some natural and synthetic therapeutic drugs. So the source, natural, would be an antibiotic, and then they have the semi-synthetic and the synthetic drugs. And in the natural antimicrobial agent, it lists the microorganism and what they make. So Bacillus can make bacitracin and polymyxins for fungi. Let's see, penicillium can make penicillin. That makes sense. So this guy named Selman Waxman found a lot of useful antimicrobials, mostly from Streptomyces. So this guy right here, look at all the drugs you can get from Streptomyces. And he coined the term antibiotics. And antibiotics just means that it's an antimicrobial drug that's produced by an organism. And remember, from these antibiotics, these natural antibiotics, the scientists can make antimicrobials called semisynthetics. And here's a semisynthetic on the chart. Ampicillin is a semisynthetic. That's an example. So, and it's just a chemically altered natural antibiotic. And when you chemically alter it, then that means that drug is not readily broken down in the body. So it stays in the body longer, so it can do its work and kill the bacteria. So the primary advantage of semisynthetics is that they are more effective than natural antibiotics. Today, most antibiotics come from bacteria, so not so much fungi. What are the desirable characteristics of the ideal antimicrobial agent, or the magic bullet? So first of all, it should be inexpensive so that everybody can get some. You want it to be stable during storage, so you can store it and have stockpiles in case of a pandemic. It would be harmless to us, and it would act really quickly. And here's a cartoon of some of the drugs that we have today and where they work on. So for example, drugs that work on synthesis of the cell wall include cycloserine, vancomycin, the penicillins, etc. So antimicrobial drugs, they'll treat infections, but they don't prevent our exposure to microbes. Both physical and chemical methods of control can help prevent infection, so we need to use both. So Alexander Fleming in 1928, he discovered the very first antibiotic. So he's growing his bacteria here, and he found this mold right here. This is the mold, and he found that the bacteria that were growing around the mold weren't there. So see this light blue spot or patch here? That means the bacteria died, and then these pieces means that the bacteria are growing and alive. So he found the first naturally occurring antimicrobial agent, and this was in 1928, but it wasn't available. They couldn't mass produce it in large enough quantities to be useful to the general public until the 1940s. But that was perfect, because then that came along at the same time as World War II, and we had antibiotics. Oh, and this is Staph, the bacteria growing here is Staph aureus. And then Paul Ehrlich found an arsenic compound that killed trypanosomes. That's the agent that causes sleeping sickness. And he also found another mercury compound that worked against syphilis, Treponema pallidum. And he called that agent that killed syphilis, Treponema pallidum, salvarsan. But mercury is toxic to humans, so you really don't want to use mercury compound to kill anything. Okay, drugs have something called a spectrum of action. It's the number of pathogens a drug acts against. So every drug has a spectrum of action. So for example, penicillin here is a narrow spectrum drug. So it's effective against gram-positive, but not really very effective against gram-negative, although it shows it in this graph that it would be. Erythromycin, you can take that for it's a broad spectrum drug. You could take it for a bacterial infection, but it may result in a yeast infection from Candida albicans. Tetracycline here is also a broad spectrum. It acts by inhibiting protein synthesis, and it's effective against gram-negative bacteria, gram-positive, chlamydias, and rickettsias. So broad-spectrum drugs may allow secondary infections to arise. For example, Candida albicans with erythromycin. It kills the normal flora, which are protective, and then you can have these secondary infections.